Swayam Prabha. Digital India. Educated India.
Okay, so let's get started. So this is lecture number 12 of this particular course on Introduction to Electronics, ESC 201. And we've been discussing circuits containing capacitors and inductors and resistors. And in this particular lecture, so the discussion has been so far, we looked at in the beginning one of the applications of capacitor, that they act as storage elements, and dynamic RAM memories are made out of capacitors. And then we've been discussing methods of analyzing these circuits containing capacitors and inductors. And today we look at another important application where capacitors play a significant role. And let me start with this statement that your watching of images and videos on mobile or TV will not be possible if capacitors had not been there. So capacitors are central to display of images and videos on mobile and present day TVs. So how is that? How do capacitors, what kind of a role do capacitors play in these applications? Okay, so here is a example of an LCD TV. LCD stands for liquid crystal display. And the liquid, so this is made up of, we will not discuss LCD much, but it's made up of an array of liquid crystal cells. Okay, and these liquid crystals have this property that the transparency of a liquid crystal cell can be altered by applying a voltage across it. So it's like a capacitor with a liquid crystal acting like a dielectric in between. And as you apply voltage to this liquid crystal cell, the transparency of that cell, the amount of light that is able to pass, depends on the voltage applied to that liquid crystal cell. So this LC liquid crystal cell acts like a voltage control light valve. You can close the valve, which means that particular liquid crystal, let's say, becomes opaque to any light, let's say, coming from behind. It becomes opaque. And then if you apply a different kind of a voltage, the valve will open and allow the light to go through. And the amount of light that goes through can be altered by altering the amount of voltage that one applies to the liquid crystal cell. So the liquid crystal display is made out of several such liquid crystal cells, and by altering the transparency of each cell, you create an image on the screen. So that's the basis of a liquid crystal cell. So we'll look at a more modern technology. Liquid crystal cells are also there, very much around us, and is the dominant display technology. The other one that is upcoming and has a lot of positive features is a display technology based on organic light emitting diode. And so many of you are familiar with the light emitting diode. The word organic means that these light emitting diodes are made out of organic semiconductors. So it has several useful properties. One of them is that you can deposit these organic materials on using a low temperature process on plastic and make flexible displays like you see over here. So our interest is not so much on the details of how an organic light emitting diode is made and its properties and all that. For us, we need to keep in mind that OLED, as we use a short form for it, OLED is also a light emitting diode, and if you apply pass a current through it, which means you apply a voltage and a current passes through it, then as a result of some of you have read this before in your school days, that when you pass a current through a light emitting diode, it's a diode, there are electrons and holes, and these electrons and holes, they recombine and the excess energy is emitted in the form of light. And so OLED is also like that. Electrons and holes recombine to produce light, except that the semiconductors are not your conventional semiconductors made out of inorganic elements, but these are organic elements that are there here. And so image is controlled by controlling amount and color of light coming out from different regions of the screen. So for example, we would have this particular display filled with lots of light emitting diodes. And by altering the amount of current that flows through each diode, you can alter the brightness of that particular light emitting diode. You can make it completely off, you can make it completely on, or you could have any number of levels of brightness in between completely off and completely on, right? And not only that, you can have LEDs which emit red, green, and blue. So you have RGB, and by combinations of how much of R you turn on, how much of green LED you turn on, and how much of blue LED you turn on, you create colors in different parts of the screen that is there here. So basically, it's a array of light emitting diodes which are switched on with different amounts of currents to give rise to create a display here. All right, so our interest is in what role does a capacitor play in this. So light emitting diodes is obvious. We need a light, something which emits light. In this case, the LCD cell is a valve. The light is behind the screen. So when you see a TV like this, there is a light behind the screen, and the valve simply controls how much light comes out. All right, so a series of light valves distributed all over all over the screen. While here we have a series of LEDs which themselves emit light, distributed all over the screen that is there here. Okay, so now, we said that to create an image, of course, you have to turn on and off LEDs to create an image, right? So different LEDs will have to be turned on to different degrees also. So if I have an array of, let's say, LEDs, sometimes we use the word pixel, a picture element, right? A pixel here. So we use the word pixel here. So let's say these are all LEDs distributed on the screen. And to create an image, you will have to turn this LED on or this LED off and this LED on, but not fully, maybe half its brightness. And like that, you'll have to, sort of program each one of these LEDs, right? To light up to the extent that you want according to the image. So if we focus on this LED, now note that to turn this particular LED on, we'll have to pass current. Right? And we need at least a pair of electrodes, one wire, let's say, coming from here, the other wire coming from here, and LED is a two-terminal device. So we'll have to turn it on. And so on the display, we have all these LEDs, but we must have wires running to circuits outside here on the left and bottom, and maybe on the right also. So we'll not. So those wires, through those wires, we'll apply current and turn this particular LED on. So note that if you want to turn a particular LED on, the word that we use is you have to address that particular LED. So each LED that is there here in this image, in this screen, has a particular address, let's say. It belongs here, perhaps to the fourth column and second row from the bottom, right? So this has an address here. So you have to send your current. If you want to turn the LED on or off, you have to send your current to a particular address. So there are various ways of addressing. Right, so we have to send it to a particular address here, and once you know, then that particular LED will turn on. So there are various ways of organizing LEDs and various ways of addressing them, lighting them up, selectively. One of them is called direct addressing. Another one of them is called passive matrix addressing, and the third one of them is called active matrix addressing here. So when you have an active matrix array of OLEDs, so we get a display called active matrix OLED display, or AM OLED display, that you would have heard of. Many of the modern mobile phones come with a AM OLED screen, right? So those are active matrix OLED displays here. So what these things mean, let's look at it in not too much detail, but at least to the extent that we can appreciate each one of those methods of addressing the LED here. So in direct addressing, each LED or pixel, we'll use it interchangeably, has its own dedicated connection to the external driver. So we have this array of OLEDs. Note that one terminal of the LEDs is all connected together, is common, right? So the blue is one terminal is common. The other one is all coming out to these drivers. These could be current drivers here. So each individual LED has its own wire running to a driver. And so if you want to turn any LED on, let's say this particular LED on, one terminal, let's say, is ground, let's say is the cathode part here, and this part here you could make it positive, anode positive, so this particular LED will turn on. Then this particular terminal here you make it 0 or you make it negative, so this particular LED will become reverse bias and this will remain off. And like that you can turn each LED on or off the way you want it. Okay, so that's called direct addressing. You have a direct wire going to each particular LED here, one from outside the display part here, outside the panel. Let's say this is the display panel. You know, all these displays are made on glass at present. So just outside you have all these drivers that are there here, right? So you have each individual LED has its own dedicated wire coming to the external world, consisting of let's say drivers, current drivers or voltage drivers, which will drive a particular amount of current and therefore turn this on. And the amount of current that you pass can determine how much is the brightness of the LED here. So this is what is shown as a simple display consisting of only 4 LEDs, D1, D2, D3, D4. So what we are saying is one terminal of the LEDs is all connected together, common, and let's say it's ground. So if you want to turn D1 on, right, if you want to turn D1 on, you pass a current here, right? You pass a current here, the current is a path, flows through this and goes here, and D1 will turn on. You don't pass any current here, you don't pass any current here, you don't pass any current here. So D2, D3, D4 are all off. So thereby you've displayed an image with one single LED on. Similarly, if I want D4 to be on, I'll pass a current here, and no current is passed here, 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 and therefore only D4 will turn on. So the point is, you know, we have selectivity. Any LED that I want to turn on, I can do that by passing a current through that particular terminal, or not passing it, or passing different amounts of current, right? So if I want, for example, an image consisting of, let's say, D2, D3, D4, all 3 of them are on, I'll pass a current here, I'll pass a current here, I'll pass a current here, and I won't pass any current here, right? Zero current. So this is off, and all 3 LEDs will be on here. If I pass more current here, D3 will be brighter. If I pass less current here, D4 will be less bright. And if I pass even less current, D2 would be even lesser bright. So thereby we can control the brightness of any of the LEDs also. And that is what we need. In order to create an image, you need to turn LEDs on or off selectively, and the degree of brightness also you need to control. And we are able to achieve that. But there's a problem. Okay. So we have freedom to turn on any combination of LEDs and any level of brightness, right? But there's a problem here. But before that, this is what we use in 7-segment displays. When you come to the lab next semester, you will see these are very, very simple displays. And so these are called 7-segment displays because there are 7 LEDs. Each one of them, A, B, C, D, E, F, G is an LED. So you can turn any LED on, A, B, C, D, and all that selectively, and display any digit here. You can display 1. To display 1, you will turn on B and C. If you want to display 2, maybe A, B, G, E, and D, right? So you can display any digits by turning a combination of LEDs on and off. So this is how these LEDs are organized. Here you see it as a bar here, but these are the LEDs A to G here. And one terminal is connected, in this case, the anode is connected to a positive voltage VDD. And we have these resistors that are there to control the amount of current. And depending on these terminals, whether you ground them or you make them positive, LED will turn on. For example, if I make D7 as 0, I connect it to ground, then this particular LED is forward biased. There's a positive voltage here. This gets forward biased, and LED A turns on here. This particular digit will turn on. And if I make the terminal D6 to D0, all of them as high, as also equal to VDD here, so none of these LEDs are forward biased, and only digit, this particular one turns on. And so like that, by applying a digital signal here, high or 0 and 1 and 0 and all that, we can display any digit that you would like here. Okay, so that's an example of a direct addressing, because each LED is directly connected to an external terminal. Each LED has one unique terminal through which you can address it. You can turn it on or off. Okay, so the problem with this is, so this is our array of LEDs. The problem with this is, let's say we have M rows of LEDs, and we have n columns, right? So we, if you want a high resolution display, you would like to have lots of LEDs to display an image with a reasonable resolution, right? So you will have, and these are often arranged in the form of a matrix like this, in this regular manner here. So let's say you have m rows and n columns. Well, we can do some calculation. The number of drivers, we said in direct addressing, each individual LED has its own dedicated terminal and a current source which drives it, right? So how many terminals do we want, and how many drivers, current drivers, do we require? Well, we'll require m into n, because each one has its own dedicated terminal and driver. So number of drivers is m into n. So let's look at a display that all of you would like to have on your mobile, a high definition, full HD color display. So there are 1080 rows, so m is 1080, and 1920 is the number of columns. And there are three, each one of them is a pixel, and each one of them will consist of a red, green, and blue, right? So the total number of external connections that have to come to the driver, if you multiply them 1080 into 1920 multiplied by 3, because in each pixel there are 3 individual LEDs, red, green, and blue. So we would require 6 million connections coming out, 6 million connections coming out, 6 million current drivers, which the calculation shows is impractical. You cannot have those many wires coming to the, coming out, and you cannot have those many drivers that are there. So it's totally impractical. But you would like to make a high resolution display like this here. So obviously what it says is, each individual LED cannot have its own dedicated driver, cannot have its own dedicated line running through the display here, because that results in too many wires, too many current sources, just impossible. Okay, so what happens is, so this is we talked about is a direct addressing. Each one has its own individual. So what we do is, we organize these LEDs in the form of a matrix, and we share rows and columns. So note that all these LEDs that are there in first row, they all have a common, connected to a common row terminal here. The blue one is a row line here. So all of them, one terminal of this LED is connected to this row, one terminal is connected here, and like that here. Okay, they all share a row. And similarly, then all these LEDs in a column, they share a column here, right? So by sharing rows and columns, so what we can do is, we can reduce the number of wires that come out from here, from this particular part here. So note that all these LEDs will share, one terminal will share one row here, and the other terminal is connected to a column here. Another terminal is connected to a column here, right? So if you have 10 cross 10 here, or in this case we have shown 1, 2, 3, 4, 5 cross 5. So you need 5 rows and 5 columns. So you need only 10 drivers, or 5 plus 5, 10 external connections, right? In this case you require, each individual LED has its own connection, so you require 25, plus there is one common, so you require 25 plus 1. So you have 25 wires running, and here you have much less. And the savings here become even greater if you try to do it with 100 cross 100. So if you have 100 cross 100 display, here you would require 100 cross 100, which means 10,000 drivers, and 10,000 wires would be running. Here there would be 100 rows and 100 columns, so it would be only 200 external connections, 100 plus 100. So 200 versus 10,000, right? So that's the savings here. So all complex displays are arranged in the form of a matrix, and the elements, they share rows and columns. So let's look at it a little bit in more detail here. So this was a direct addressed, or simple 2 cross 2 LED display. So this was direct addressing. Each individual LED has its own connection. But now we are going to arrange them in rows and columns, right? So, and share connections. So note that now savings will not be obvious because it's a very simple display here. But what has happened is, this LED's cathode and this LED's cathode, they are all connected together into a what we call as row 1. And this LED D1 and D3, they share a column here, right? So we call it column 1 and column 2. So in this case, note that in this case you require 4 external terminals, in this case also 4 external terminals, and that's because it's only 2 cross 2. But then, as we just said, if you immediately start doing it 1000 cross 1000, you will see that the number of external terminals here would be 1000 plus 1000, 2000. while here 1000 across 1000 will become number of terminals will become a million, right? So a million versus 2000. So this is manageable. When you have 1000 connections coming from here, 1000 connections coming from here, so that we can manage those number of connections and those number of wires. But a million connections, a million wires, that is unmanageable, right? So that's the savings that we get by arranging it in the form of a matrix and connecting our LEDs to in the form of rows and columns, right? Okay, so number of drivers m into n here, number of drivers is m plus n here. So huge saving, especially as you go to larger numbers of m into n, so high resolution. So all high resolution displays are connected in the form of a matrix with rows and columns. All right, so let's see, if you share, then you lose flexibility because each individual LED does not have its own unique terminal here, because D1 and D3, note that they share the same column line, and D1 and D2, they share the same rows. So because of this sharing, some limitations come. So suppose D1 has to be turned on. Well, you can turn D1 on. I can take this row, make it ground, and I can pass a current. But then I want this current to go through D1. I don't want this current to go through D3, right? Because now note that D1 and D3 share a column. Now I don't want current to flow through D3. So what I do is I apply a large positive voltage here. So effectively what it does is it reverse biases this particular diode. And because it's reverse bias, nothing flows here. So the current that I passed at this particular column then goes only through D1. It cannot go through D3. So thereby, by making this row ground and this row positive, I arrange the current to go through D1 and the LED D1 lights up. Okay, so far no problem. Suppose D4 has to be turned on. So what do? Only D4 has to be turned on. So what we will do is we will pass a current through column C2 and we will ground row R2, right? So let's do that. We'll ground row this one here and we'll pass a current here. Now we want this current to flow only through D4. We don't want it to flow through D2, right? So we need to reverse bias D2. So we apply a positive voltage here. So that reverse biases the diode D2, and so the current only flows through D4. So that's also good. So we've been able to do that. Okay. But suppose both D1 and D4 have to be turned on. So my image requires that this LED should be on and this LED should also be on. So what do? If I want this LED to be on, I have to pass a current here because all current comes from external terminals here. And we'll have to make it ground because the current has to flow like this here. If I want D4 to be on, I will have to pass a current through here, through this column, and it has to flow here, so I'll have to make this also ground. But then what do you see? Well, this current that sees here, it will not only flow through D1, but it will flow through D3 also. So what will happen is this current, which was intended only for D1, now gets shared between D1 and D3. So D3 also turns on. And the current which was meant for D4, it flows through D2 also, because one terminal is ground, and this current, why should it only flow through D4? It should flow through D2. Note that all LEDs are the same. They're all identical, right? So the current would flow here. So you wanted D1 and D4 to be on, but then you get all 4 LEDs on and you don't get the image that you want here, right? All 4 LEDs on instead of only D1 and D4 on. So now we have a problem. How do we get D1 and D4 selectively to be on and D2 and D3 to be off? So the only way we can do that is because by displaying the data, whatever image is nothing but a data. And so whatever data you want it to be displayed, you do that row by row, right? So what we do is the following. We row by row. So what we do is we select first row. We go row 1, R1, R2, R3, R4, and so on and so forth. So we select row R1. When we select a row R1, we will make it ground. And then whichever LED you want it to be on, you pass a current. If you want this LED to be on, you pass a current. So when you select a row, you make it ground, and all other rows that are there, you will apply a high voltage here. So all other rows, all other LEDs will be reverse biased. So the current that you apply from here only goes through this LED and it turns on. Now, so once you're done with row 1, then you go to row R2, right? And row R2, and all other rows will be reverse biased. R1 will be reverse biased here by applying a positive voltage. And now you wanted D4 to be on, so you pass current through D4. So D4 turns on. But note, we have a problem. We wanted both D1 and D4 to be on. But now what we did was, we first selected R1 and we turned this D1 on. Then when we went to the next row, the D1 turns off because there's no current being flown through it. It is reverse biased. Then we turn D4 on, right? Now what we can do is, this is called one frame of an image. You go from one row to the last row. So you turn D1 on, then D1 turns off, and then you turn D4 on, fine? And then you go back to row R1 and turn D1 on again. And then you go to D4 and you turn it on again. And like that, if you do rapidly enough, right? So if you do it rapidly enough, you go to R1, light up D1, go to R2, light up D4, then again go back to R1, light up D1, then again go to R2, light up D4, and you keep on doing it. Now, if you do it, if you do it fast enough, the eye is not able to perceive this, that D1 is switching on and off. So the eye will average it out, and to the eye, it will appear that D1 is on and D4 is on. And D2 is off, and D2 and D3 will remain off, of course, because we didn't pass any currents through them. So that way, we are able to display D1 and D4 to be on here, right? So in a 2x2 matrix, what is happening is D1 is being turned on, then it is off. Why it is off? Because we have gone to the second row. Then after we have finished with 1 and 2 rows, we come back to the first row and we turn it on, right? So it goes like this here, okay? The problem with this is, so we have, by displaying the data row by row, and we are saying if you do it fast enough, then the eye will see, I will average it out, and you will get the right image on the screen here. But the problem with this is, if I turn D1 on like this here, and then when it goes to the next row, D1 is off, and then I turn D1 on, the eye will average it out, and I will see an average brightness, which is L1 by 2. Whatever is the brightness of the LED, it will see L1 by 2. Whatever is the brightness of our D2, it will see only L2 by 2 here. So average brightness of the two LEDs will be 0.5 L1 and 0.5 L2. So now you can see a problem. With 2 rows is okay, the average brightness has become 0.5. And so if you want the eye to see a brightness is measured in units of candela per meter square. So if you want the eye to see a brightness of 100 candela per meter square, well, then L1, the LED has to be lit up to a brightness of 200 candela per meter square, twice as bright, so that the average brightness is 100. So now suppose we have 3 rows and 2 columns, right? So we have 3 rows. So what will you do? How will you display the image? You will select row R1, and let's say D1 will be lit up, and then accordingly, then you will go to row R2 and row R3. Once you're finished with the whole row, we say 1 frame of image has been displayed, and then you go back to the first row, right? So the display will go like this here. So if I'm focusing on D1, D1 will be on for a certain time, then will be off for the time when you go to row R2, will be off when you go to R3, and then again back, you light it up. So what will be the average brightness here? Well, if this is the brightness, peak brightness is, let's say whatever it is, the average brightness will be 1/3. Right, so this causes a problem, as you can see here. If I start getting large number of rows, now we said for high resolution displays, for your full HD display, you have 1000 rows, 1080. So when you have large number of rows, well, what is the problem that we get? Well, the LED is on for a very short period of time during the time that particular row is selected, and will remain off as you go to the second row, third row, fourth row, and to the 1000th row, and then it will turn on again, right? So the average brightness becomes very low, right? Average brightness. So if I have, let's say, 480 rows, 480 rows just for the sake of discussion, and you want an average brightness of 200 candela per meter square, the peak brightness will be 200 multiplied by 480, so it will come to around something like 10 to the power 5. So the LED is on for a very brief period of time, but then it has to be super bright, extremely high brightness level of 10 to the power 5 candela per meter square to create for the eye an average brightness of 200 candela per meter square. So you're driving the LED very hard. You're driving lots of current to create that high brightness, and that becomes very difficult. The LED starts to degrade and it's not able to handle that much current. So to create very high brightness, you'll have to pass very high current, and the LED is not able to handle that. And therefore, you are not able to make displays with large number of rows. That becomes difficult. So even going beyond 100 rows or 150 rows, it becomes very difficult. So if you're looking for 1,000 rows and 1,000 columns, well, you can't go through this particular approach here. And so the solution to this particular problem is what we call as the active matrix OLED display here. So so we have an OLED display arranged in the form of a matrix. So the previous display that we have talked about is what we call as is a matrix display. We call it a passive matrix. Passive because it does not, in electronics we use the term active to denote a transistor. And when circuits don't have a transistor, we generally call them a passive circuits here. So in this circuits, we don't have any transistors, so it's a passive circuit. And we call it a passive matrix display. Display is obvious, matrix because we've arranged them in the form of rows and columns, and passive because it does not contain any transistor anywhere in my display device here. So that's why it's called passive matrix display. So these passive matrix displays, as we have just said, you cannot make high resolution display because to achieve a brightness of, let's say, 200 candela per meter square for I, each individual LED will have to be driven to for 1,000 rows will have to be driven 1,000 times higher brightness, and that becomes almost impossible to do it. The LEDs cannot handle that much current and that much brightness. So the solution to this is what we call as active matrix display. So, all right, so let's come to active matrix display and let's understand why is it we require what is the main problem with the passive matrix. So as I said again, if the eye requires a brightness of 200 candela per meter square, then the peak brightness from the OLED, if you're making, let's say, one number of rows is 1024 into 1024 columns. So depending on the number of rows, the peak brightness from OLED will be 2 into 10 power 5. And why is it that you require such a high brightness? Because we said the data is displayed row by row. So first you select a particular row and you light up an LED. And then when you go to the next row and the third row and the fourth row and the 1,000th row, this LED is off. This LED is off, right? And that's the reason. And because it's off most of the time, when you light it up to a very high brightness level. So to prevent this problem, I don't want to drive my LEDs to this much brightness level because they can't handle it. So if my display requires a brightness of 200 candela per meter square, I would like to light up this LED to 200 candela per meter square. But then we note that as we go to the next row, this LED will turn off because the current and all that is intended will go here. So the solution to this is keep the OLED on even when it is not being addressed. So the idea is, let's say you light up this OLED to 200 candela per meter square. Then when you go to the next row, we don't want it to switch off. We want it to remain on to 200 candela per meter square. If this one is, let's say, 150 candela per meter square, a different brightness level, when you go to the next row, I want it to remain at 150 candela per meter square. Not only to the next row, but to the third row and the fourth row and the fifth row, I want it to remain at 150 candela per meter square. Right? So once you select an LED, you turn it on to a certain degree, you want this LED to remain at that particular level. Now, how do you ensure that? When you're sharing the columns and rows and all that, how do you ensure that once turned on, it remains on at that particular level of brightness? All right, so this is how we do it. So each element that was simply an LED, now we use the word pixel. So each element is replaced by this small circuit that you see here. So we have this LED. So earlier this was simply an LED with two terminals. Now we have an LED, we have a transistor, we call it a thin film transistor. So let's not get into details of that. It's a transistor. So we have one transistor here and we have one transistor here and we have a capacitor. Now you can see where the capacitor plays a central role, because we said once it is 150 candela per meter square here, that 150 candela has to be remembered, so that when you go to the next row and the third row and the fourth row, it remains on at 150 candela per meter square. If some other one LED is 175 candela per meter square, well, that 175 candela per meter square has to be remembered, and that value has to be remembered, and the LED has to be on at that particular brightness level. So there is there's a brief period of time when you're going to select this particular LED by selecting a row and a column, and you'll program it to be 200 candela per meter square. But then when you go to the next row, you're no longer selecting that particular one. That particular pixel has to remember now that it is at 150 candela per meter square. It has to remain at that 150 candela per meter square. So this is the circuit that is able to achieve this. So let me explain using our, again, simple example of 2x2 display here. So our display now consists of an LED and these two transistors and a capacitor. And yeah, so each pixel, so instead of one LED, we have this small circuit that is there here. And now you can see why we call it an active matrix OLED display here, because we have these active elements here. We have these active elements, these transistors that are present. Of course, it's arranged in the form of a matrix. We again do row by row. Because why do we do row and column sharing? Because we cannot have that many external connections, that many drivers, so we have to share rows and columns. And to solve the problem of high brightness level that was required, we've used a transistor here. So how does it work? Okay, so let's so again we do row by row. So note that let's say we have selected row number 1, first row. So selecting, we apply a high voltage here, let's say 10 volts. So what this 10 volt will do, will turn this transistor on. It's like a switch. So this particular transistor will be on, and this particular transistor will be on here, right? So both these transistors on. Now you want this LED to be on and this LED to be off, right? So what we do is this LED to be on and this LED to be off. So on this column, we apply the data. So we apply 5 volt. So note that, and all other rows are not selected. So you give them 0. So when you give it 0, this switch is off, this switch is off. So all of the rows are now, we apply 0 volts and all these switches are off. So when you apply a voltage at this particular column, this voltage goes only to the selected row. It will not be able to go anywhere here because this switch is off, right? So this 5 volt will go through this switch and will charge up this capacitor here. So that's where our RC charging comes into picture here. The transistor, when it is on, it has a certain amount of resistance, so there's an RC charging and the capacitor will charge up. And it will charge up to what? 5 volts. Because we have applied 5 volts here, so it charges up to 5 volts. Now this 5 volts goes to the gate here, and we've discussed the operation of a MOSFET. This 5 volts will cause a current to flow here. Will cause a current to flow here, and the LED will light up. Okay? Now if you wanted LED to be let's say on to a smaller degree, maybe we would have applied 2.5 volt here. So when 2.5 volts goes here on this capacitor here, 2.5 volt will cause lesser current to flow through the transistor and the brightness of the LED will be less here. In this case, we don't want this LED to be on. So what we do is we pass 0. When we pass 0 here, this switch turns on. And even if this LED was on earlier, let's say it was on earlier, and let's say there was some charge on the capacitor will immediately discharge to 0 through this switch here. Capacitor will discharge and this LED will be 0. So thereby what we have done is, by selecting this particular row and by applying the data in the columns, we have programmed the LED to be on off to various degrees by altering the voltage here. So we have programmed this to be on to a degree 5 volt and to a degree 0 volt here. Now we go to the next row. Okay, so these are switches are on and 5 volt will go here and all that, and these are all off. So now we go to the next row. So when we go to the next row, when we go to 10 volt here, we are selecting the next row here. Now what is important is look at what has happened to the first row. So first row, when first row is off now, right? When you select this, so 10 volt, so this is off, so TFT is off here, the transistor is off. And this 5 volt that you put on this capacitor here, it stays there because there's no path for the capacitor to discharge. So this 5 volt stays there, and this 5 volt will keep on causing current to flow and the LED remains on. So remember, this was our task. We said that we have to keep the LED on to, let's say, 200 candela per meter square. Even when we go to the next row and the third row and the fourth row and the fifth row, the LED should stay on, and then it stays on by this means here. The capacitor cannot discharge. And note that that's why the capacitor acts as a memory, 5 volt. If I had put here 2.5 volt, the capacitor would have kept a charge equal to 2.5 volts. And accordingly, a certain current would have passed here, and a certain brightness would have been achieved here. So that's how what you do is you select a row and you program this particular capacitor to a particular charge, to a particular voltage, and that turns on the LED to a particular brightness. And then you go to the next row and you want this LED to be, so now these TFTs will turn on and you program them. You program them to whatever level of brightness you want, and thereby you're able to do that, and then you're able to make a complex high resolution display. And the capacitor is playing a central role here. The capacitor stores the charge, acts as a memory. This charge on the capacitor decides how bright is this particular LED is going to be. So your image, whatever is your image data, the data is stored on the capacitor, and the capacitor decides the brightness of the OLED and decides the image that is displayed on the screen. So capacitor is central to a display like this, AMOLED display. And I want to show you a particular pixel of a display. So there is a light emitting diode which emits light and creates an image, but the capacitor decides, along with the TFT, the capacitor decides how much light, how much current is able to flow through the LED, and what is the brightness of the LED. And the capacitor maintains the image that is there on your screen here. So capacitor is central to active matrix OLED display, and I've not talked about LCD, but similarly capacitor is central to active matrix LCD display. So all your modern flat panel television screens, whether it's a TV or a mobile, will not be possible but for the capacitor. Capacitor is absolutely essential here. All right, so let's stop here.